Assalamu alaikum dear students. We are discussing the relations, and in previous lecture we discussed the types of relations. One, we discussed the reflexive, the universal relation, and second one, the empty relation on a set. Now today we are going to discuss few more types of the relation on a set. Now the first one is here, the reflexive relation. Now what is reflexive relation? Let us assume that R be a relation on a set A, where A is non-empty set. Then this relation R is said to be a reflexive relation. If AA belongs to this ordered pair, AA belongs to R for all elements of A, means that for all A belongs to A. So this means that if A belongs to A, this should imply that this ordered pair AA belongs to R. This means that each and every element of A is related to itself. Now the second one is the symmetric relation. This relation R on A is said to be symmetric relation if there exists an ordered pair AB belongs to this relation R. This should imply that BA belongs to R. If this happens for each and every element of R, means for each and every ordered pair, that is the converse of this or the reciprocal of this ordered pair belongs to this relation also, then we can say that this is this symmetric relation. Because A, B and BA, there is symmetry, that is why this relation is called as the symmetric relation. Now the third one is the transitive relation. Now the transitive relation R on A is said to be transitive relation if there exists two elements of this form, AB and BC, which belongs to R. This should imply that AC belongs to R. That is, whenever A is related with B, means AB belongs to R. B is related to C, means BC belongs to R. This should imply that AC belongs to R, means A is related to C. Then we say that this R is transitive relation. Now if relation is both these three types, that is, if R on a set is reflexive, it is symmetric, it is transitive, then we say that R is an equivalence relation. So equivalence relation is that relation which is both a reflexive, symmetric and transitive in nature. Now we will explain, or I will explain usually these three types, that is reflexive, symmetric, transitive and these equivalence relation through the examples. Now if we consider A, set A, which is non-empty set, and if we consider R a relation on A, means R is a subset of A. And if R is, suppose R is phi, because every set, every this subset is subset, this phi is subset of every set, means if we consider R equals to phi, which is subset of A cross A, then clearly this is non-symmetric, this is non-reflexive in nature. Why non-reflexive? Because A is non-empty, there exists at least one element. So if we assume A belongs to A, it does not imply that this ordered pair AA belongs to R. AA belongs to R because R is empty set. That is why this is non-reflexive in nature. So any this empty set or empty set on any non-empty set, if we consider this to be a relation, then clearly it is never this reflexive relation because this is non-empty. Similarly, if we consider R a universal relation on A, if R is this universal, means if R equals to A cross A, this is a universal relation. Clearly it is reflexive in nature because it contains each and every ordered pair with first entry from A and the second as well as from A. So this means that in particular it contains the ordered pairs of the form of AA. It contains ordered pair of the form of AA for each and every belongs to A. So this means that whenever for each and every element A, ordered pair AA belongs to this R, then we say that it is a universal, this reflexive relation. Here this universal relation contains each and every ordered pair. So this is clearly a universal relation. Now we will consider the example on proper this relation. If A equals to 1 2 3, if A equals to 1 2 3 and R equals to 1 1 1 2 2 2 2 3 and 3 3. Here A contains three elements, that is 1 2 3. Now if this OR is reflexive, then it should imply as that for each and every element 1 1 2 2 3 3 should belongs to this OR. Clearly from the given definition of OR, we have 1 1 because 1 belongs to this implies that 1 1 belongs to this OR. 2 belongs to A implies that 2 2 belongs to this OR. 3 belongs to A implies that 3 3 belongs to OR. So this means that for each and every element under and through this relation, that element is related to itself. So this means that it is reflexive in nature, or it is a reflexive relation on the set A. Similarly, if we consider R equals to 1 2 2 2 3 2 1 1, here 1 belongs to A, 1 1 does not here 1 belongs to this R. For 2 2 2 belongs to this, but this A contains 3, while as 3 3 does not belong to this OR. So this means that there exists an element which is 3 in A such that 3 3 does not belong to OR. So we can say that this OR is non-reflexive on this A. So this was about the reflexive relation. Now if we consider the symmetric, for symmetric, if OR equals to on any set, on non-empty set, we define a relation on A as OR equals to 1 1 2 1 1 1 3 2 2 3. Now here this OR contains 1 2 3 4 5 elements. The first one is 1 1, first one is 1 2, first one is 1 2. Now 1 2 belongs to OR. Now if OR is symmetric, it should imply that 2 1 belongs to OR. Here clearly 2 1 belongs to OR. Similarly, if we consider 1 1, the reciprocal of this 1 1 is again 1 1. So in set terminology, this repetition is not allowed. So this means that for 1 1, 1 1 belongs to this OR. Similarly, 3 2 should imply that 2 3. Here we have 2 3. So this means that from this OR, we can say that if AB belongs to OR in general, this implies that its reciprocal, that is BA, or the converse. Usually we say the converse. This BA belongs to OR. So OR is reflects this symmetric on A because there is symmetry between the ordered pairs. Or if we consider OR to be 1 5 5 1 2 3, here 1 5 belongs to OR implies that 5 1 belongs to OR. 5 1 belongs to OR implies that 1 5 belongs to OR. Here 2 3 belongs to OR, but there does not exist 3 2 because this OR contains only 3 elements, or this OR has 3 elements. So 3 2 does not belongs to OR implies that OR is not symmetric in nature because there exists an element, this 2 3, which belongs to OR, but its converse means BA does not, means 3 2 does not belongs to OR. That is why we say that this OR is not symmetric. If OR is 5, then clearly OR is symmetric in nature. Why? Because if here OR is 5, means there does not exist any element. Hence we cannot say that if there exists an element, while as its converse, means if AB belongs to OR, we cannot say that there exists an element AB which implies that BA does not belongs to OR because OR is empty set. So that is why this OR is always symmetric in nature. Similarly, if we consider this universal relation on any set, then clearly it is symmetric in nature because there exists each and every ordered pair in that very relation. Now we will discuss this another type, that is third type, that is transitive relation. If we have the set which is non-empty, that is 1 2 3, then A cross A is 1 1 1 2 up to 3 2 because it contains 9 elements, which are these elements. Now let us define a relation OR, means OR we define a subset of this A cross A as OR, which is 1 1 1 2 1 2 2 1. Now clearly transitive means if we have the elements of this type A, B and B, C, so this means that there should exist an element of this type A, B and B, C. If these two elements belongs to this OR, it should imply that this element AC should belongs to this OR. Means if there are two elements of this type, this should imply that there is another third element, or the third element of this set is of this type, that is AC. Here 1 1 belongs to this, 1 2 belongs to this OR. Now clearly 1 2 also belongs to this OR. So 1 1 1 2 implies that 1 2 belongs to OR, hence OR is. Also we have 1 2 and 2 1 implies that it should imply that AC means 1 1 belongs to OR. So this means that there are the elements of this form AB and BC, which implies that AC belongs to OR. So clearly this OR on any set means on OR on this A is transitive in nature. Now if we consider OR to be 1 2 and 3 2, 1 2 and 3 2, OR is here also transitive. OR is here also transitive. Why? Because if we consider this set, this very relation, this one, here OR is 1 2 and 2 1. This there are elements of this type A, B and B, C, but there does not exist element of this type AC. Here 1 2 and 2 1 should imply that 1 1 belongs to this OR. Then we say that it is transitive, because here 1 2 and 2 1 belongs to this OR, but these two elements does not imply that 1 1 means AC belongs to this OR. That's why this is transitive. This is non-transitive. This is non-transitive. Here there does not exist any element of the form of AB and BC through which we can say whether AC belongs to or AC does not belongs to. So from this reason we say that this OR is also transitive in nature. This OR is transitive in nature. Why? Because there does not exist, we cannot say that these two elements belongs to this, but it does not imply that third element belongs to this. So from this we can say that this R equals to phi is also this means when we consider empty relation, that is also transitive in nature, because this R does not contain any element, hence in particular it does not contain into the elements of the form of A, B and BC, which implies or which does not imply that AC belongs to this. So R equals to phi is also transitive in nature. Now if we consider this universal relation is always transitive in nature. So this was about these three types: reflexive, symmetric and transitive relation. Inshallah in tomorrow's lecture we will discuss the equivalence relation and examples on equivalence relation. So thank you.